Welcome to lectures 18. So today we will talk about source coding one algorithm, that is the Huffman code. But before that, let me first give you one example that how this variable length code is more beneficial compared to the fixed length codes. For example, let us take a couple of this is the symbol set, suppose, for the random variable which is emitted, say A, B, C, D. Okay, and assume the probabilities are as follows. So probability of A is equal to 0.6, probability of B is equal to say 0.2, probability of C is equal to say 0.1, and probability of D is equal to say 0.1. So this is total probability is 1. Now fixed length code, suppose regular binary encoding. So fixed length code will assign the following codes. So A will be assigned to, say, CA is the code, is say 00, CB is say 01, CC is say 10, and CD is say 11. So in that case, what is the expected length of the code word? Expected length is essentially 2. You don't have to even compute, because all of the random variable, the values the random variable take are 2. So in this case, so suppose that one symbol is emitted every say 1 millisecond or something like that. So suppose T symbol, so this is symbol time. Suppose this is 1 millisecond, then what is the bit rate? So R, this is the bit rate, say it will be 2. So 2 symbols per 1 millisecond, so this is 2 kbps, 2 kilobits per second. Now I'll assign a different code, say variable length code. And let us assign the following. Say CA is equal to say 0, CB is equal to say 10, CC is equal to say 110, and CD is equal to say 111. So I am assigning 1 bit, 2 bits, 3 bits, 4 bits. So LA is equal to 1, LB is equal to 2, LC is equal to 3, LD is equal to 3. So what is the expected length? It will be 1 into LA into PA, so 1 into 0.6 plus 2 into 0.2 plus 3 into 0.1 plus 3 into 0.1. So that will be 1.6 bits per symbol. It's 2 bits. So if I ask the bit rate for the same time, so bit rate will be 1.6 kbps. So you can see that the rate is decreasing. And if you like, yeah, so variable length code will always give you a better like chance of reducing the bit rate, and that will like be beneficial for when we are going for some high definition digital communication. So our objective is always to decrease the like bit rate which is going out of the source. Now with this I'm going to the like first theorem, we can say, about entropy. We can talk about the entropy bound basically for the source code. So in the last class for using the Lagrange multiplier, I have shown you that how the lower bound of like expected code length is essentially the entropy of the source. Today I'll put the upper bound as well. So let us derive the entropy bound of the expected length. So the entropy bound, which is the expected L, I can say the minimum of that will be always within Hx. This is expected length, the minimum of this. I can write this to be L mean or something like that, L mean, and this will be greater than equal to Hx. This we will prove first. This one we have shown, but that Hx happened only when you like take that L can take any real value. But today we will show you that even for integral values Hx can be obtained, but there is a condition. So actually this is this requirement, this equality will happen. So this L mean will be equal to Hx only if every probability, say Pj, is having some form 2 to the power minus Lj for some integral value of Lj, and this should be true for all j is equal to 1 to m. Only then this equality is satisfied. Let us prove that. So assume the lengths are L1, L2 up to Lm are the lengths, code lengths. Okay, so the random variable capital L basically takes values from this set. So this is the set from where the random variable L, this is the random variable of the random variable of the length of the code word, and L takes value from this. Then what is Hx minus L? This will be Hx is summation Pj log 1 by Pj, j is equal to 1 to n, minus summation Pj Lj, j is equal to 1 to n. So I can take Pj as a common, j is equal to 1 to m, and this will be log 2 to the power minus Lj divided by Pj. So now I will use one inequality of logarithm. So this will be, this I can write as log of E into summation j is equal to 1 to m Pj into ln 2 to the power minus Lj divided by Pj. And now if you plot the curve of natural logarithm, that will give you an immediate inequality. So natural logarithm is like this. So this is say u, natural logarithm is like this. That's the curve of natural logarithm, ln u. And if I plot a straight line at this point, the straight line is say u minus 1. So you can see that ln u is always less than u minus 1, and the equality arrives only when u is equal to 1. So this is u, this is say u is equal to 1. So your ln u is always less than equal to u minus 1, and this equality arrives at u is equal to 1, ln u is equal to u minus 1 is equal to 0. Isn't it? So this inequality we will use here. So this will be less than equal to log E summation Pj into 2 to the power minus Lj by Pj minus 1, j is equal to 1 to m. Now this is equal to log E summation 2 to the power minus Lj minus Pj, j is equal to 1 to m. Now the first part is the Kraft inequality. So that is less than equal to log E into, the first part is less than equal to 1 and second part is obviously 1. So this is less than equal to 0. So this side is established already. So the one side is established, Hx minus L is less than equal to 0. Okay, or Hx is less than equal to L. Now when the equality will happen, so equality, So equality will arrive here. This will be equal if this is equal to 1, this is equal to 1, u is equal to 1. So 2 to the power minus Lj is equal to Pj, and that will ensure the equality of the Kraft inequality as well. So equality will arrive if 2 to the power minus Lj is equal to Pj for all j, or I can say Lj is equal to log of 1 by Pj. So if that is the case, then the equality arrives. Now if not, if this is not the case, then I can assign Lj to be the ceiling of log 1 by Pj. So if that is fraction, not an integer, then I can assign the ceiling. So I can write Lj to be less than log 1 by Pj plus 1 and greater than equal to log 1 by Pj. That I can write always for whatever values of Pj. So this side is basically the Kraft inequality, you can say, or this side is whatever we have established right now, but this will give you the upper bound. So what I will do, I will basically multiply this with Pj. So this is true for Pj is a positive number, non-negative number, so this is correct, and this is true for all j, so I can take the sum. J is equal to 1 to m, j is equal to 1 to m, j is equal to 1 to m. J is equal to 1 to m. So what is this? This is, and this is hx plus this is 1 and this is hx. So that is my inequality, the bounds are established. So this is done. With this we can move towards, okay, so this basically gives me some method for describing or like making the code. So that method I can write down in a fashion. So the methodology using the like finding out Lj from here, so Lj can be found out from here, and then using the second proof of the sufficiency proof of the Kraft inequality will give me a method. So the method can be established like this. So for the symbols, say a1 to am, where the probabilities are p1 to pm, find. So I am writing the method like this. So write down this pj's in non-increasing fashion, increasing way. Then obviously Lj, which is equal to ceiling of log 1 by Pj, they will be non-decreasing. Then assign Uj is equal to summation 2 to the power minus Lj, j is equal to 2 to the power minus Lic, I is equal to 1 to j minus 1. So for all j is equal to 1 to m. The first value u1 is equal to 0, of course. Start with u1 is equal to 0. Then you find all such real numbers u, and you can see clearly that these i's are not really real number, they are rational numbers. So they have finite Boolean description. So find out that description, find out the finite Boolean description, and they will have the lengths Lj's corresponding to. So that will be one code. But this code is this optimal? Not really, because this inequality, whatever we have found out, this hx plus 1 is pretty loose. It is not really that tight. If they are having this characteristics where the mean L mean is close to hx, then we are good, but not always. If that is not the case, if this is not the case, then if I use the upper bound of L, the mean of L, which is hx plus 1, hx plus 1 is not that tight. I can show you one quick example. For example, the values I have chosen over there, suppose this one, 0.6, 0.2, 0.1, 0.1. Here arbitrarily assumed some lengths like 1, 2, 3, 3. That's good. But if I follow this technique, Lj is equal to ceiling of log 1 by pj, then what values the corresponding codes will take? Let us check that. So suppose the probabilities are 0.6, 0.2, 0.1, 0.1. So this is written in a non-increasing way. Then what are the LJs? So L1 is equal to ceiling of log 1 by 0.6. So 1 by 0.6 is some 1 point something. So which is again the value is a fraction. So ceiling of that is 1. So this is fine. What is L2? L2 is ceiling of log 1 by 0.2. So that is log 5. That is 2 point something. Ceiling of that is 3. L3 is log of 1 by 0.1. That is log of 10. Log of 10 is 3 point something. Ceiling of that is 4. L4 is similarly 4. So this is 1, 3, 4, 4. So what is the average length? Average length is 1 into 0.6 plus 3 into 0.2 plus 4 into 0.1, 4 into 0.1. And you see it is actually 2. So it is as good as fixed length encoding. So it's not really good. And if you compute the hx for this one is definitely much less than 2. It is close to some 1.4 something. I have to compute. You check it. Hx you compute pj log 1 by pj. J is equal to 1 to 4. This will be much less. So of course this L min is obviously less than hx plus 1, but hx plus 1 is not that good like bound for computing this L min. And you can clearly see this arbitrary description 1, 2, 3, 3 is much better compared to 1, 3, 4, 4. So why are you wasting one bit like here, here and here? That is not required. Like your tree is not that good. So if you construct some tree using this, the tree will be like this. So this will be 0 say. So for like A1 I assign the code 0. So this is A1 is equal to 0. C A1 I can write. Second is say 1. Then the assignment is say 1 0 0. So it is say CA2 is equal to say 1 0 0. And next are 1 0, say 1 0 and 1 1. So say CA3 is equal to 1 0 1 0 and CA4 is equal to say 1 0 1 1. So clearly this tree is not full because you are wasting this one line and you are introducing this 0 which is unnecessary. So you are wasting much space in terms of the tree. Okay, so just following this method is not giving you an optimal result. It is ensuring that you can create one like code which will satisfy this inequality. Definitely the L min will satisfy this inequality, but this side is not that tight. So we need a better code, and that better code was developed by David Huffman. So let me talk about that. So this is a curious story actually. It was in MIT in Professor Fano's class. So Fano was contemporary of Shannon, who was also like contributing in information theory, the earlier development. So Professor Fano was teaching about this Kraft inequality and this optimal code description and entropy and etc etc. And David Huffman was an undergraduate student in his class. It was undergraduate class actually. So Professor Fano asked them that can you find out some code which will be optimal in some sense in terms of the average code length. expected code length. And what Huffman did, he observed some principles, some lemmas in terms of the behavior of the code, and he developed an recursive algorithm, and that algorithm is basically not even considering the Kraft inequality and the entropy. So even without that, just from the probabilities itself, the PMF, the probability mass function, he developed the algorithm. And now I am going to first describe the observations of David Huffman, and then I will describe the algorithm. So Huffman observed, which you have already observed, so I am just reiterating that. So he observed, so I am writing lemma 1c. He observed that all optimal code should have this following property. Code has the property that if pi is less than pj for some ij, that will imply li is greater than equal to lj. Okay. So this is obvious because the way p and l are related, it is like this log 1 by pj is basically minus log pj, right? So they are monotonically decreasing or non-increasing function of each other. So if lj increases, pj decreases, or on the other way around. So if pj increases, lj decreases, or pj decreases, lj increases. So he observed that optimal code always has this property. So how did he prove it? He proved it even without taking into consideration the relationship between lj and pj. He doesn't. He really did not care. So he told that assume on the contrary. Suppose pi is less than pj and li is less than lj. Okay, so suppose this is the code C. So in the expression of average length, so there will be different terms, but the terms corresponding to these two code words I and j, ai and aj, the corresponding terms will be pi li plus pj lj, and there will be some other term where the corresponding probability and length values are entering from the other symbols, but corresponding to these two symbols I and j, the terms will be this. Now assume there is another code word, and you assume that this is the optimal code. This is having the minimal length. So this is the minimal length. Now assume a second code say C dash, where you just swap these two code words for I and j. So swap C say ai and C aj. Then the length of this will be lj. So since you are swapping, so C dash aj ai is basically C aj, which is your lj, and C dash aj is C ai, which is li, which is having length li. Yeah, I should not write this. So this is the swap. So now I can write that L dash ai is equal to lj and L dash aj is equal to li. I am swapping them. Then what is the average length for this? The remaining thing is same. I did not alter anything, but I alter only these two. So it will have the probability remains same. So for ai the probability is pi, but length is now lj, and pj the length is now li. I will show you that this is less than this. So this cannot be the minimal and this cannot be the optimal. So L hat dash minus L dash, I will show that this is less than 0, is equal to, this cancels out, the rest cancels out. So it will be equal to pi lj plus pj li minus pi li minus pj lj, which is equal to, so if I take pi common, pi is into lj minus li minus Pj into Lj minus Li. So I can take a like common, so Pi minus Pj into Lj minus Li, which is equal to, so what you assumed? You assumed this, so Pi minus Pj is negative and Lj minus Li is positive, so 1 negative into 1 positive, so this is negative, less than equal to 0. So obviously you establish that, it is not less than equal to 0, it is strictly less than 0, because both of them are less than. So you establish that the new one, so from here you establish that the new one is basically less than the old one. So contradiction. So this cannot be true. So this is correct, obviously. So this is the first observation, and this is some guiding principle that whenever the probability decreases, your length increases, and that makes sense, because information theory, you know that when something is less likely, that is more information. So more information means you have to give more number of bits. Okay, the second observation, what he observed, that the tree has to be full, the corresponding tree has to be full. That also makes sense, because if it is not full, you can either reduce the length. So the second lemma, there is nothing to prove actually. So the code tree of an optimal code is full. So if it is not full, so proof, I can say that if it is not full, reduce a corresponding code word. Reduce means shorten basically. So you will get some node like this, where this thing will not be there, the other branch is not there. You just remove this, that is good enough. The third one is that he observed. So let me define something called sibling. So let me define something called sibling. Sibling is basically brother or sister, you can say. So sibling is basically two codes which are coming from the same parent node. So they differ only in the LSB, in the least significant bit. So two code words which differ only in the LSB are called sibling. Okay, so for example, 0010 and 0011, they are sibling. So the third lemma says that if you assume the following order, P1 is greater than or equal to P2, so this is a non-increasing order, Pm minus 1 is greater than or equal to Pm. If this is the order, then the following two code words, Am minus 1 and Am, are siblings and have the maximal length. This is again very much intuitive, that as probability is decreasing, the length should increase. So the last two should have the maximal length. Okay. So prove how I can say. I can say that if Pm is less than all Pj's, then obviously the corresponding length will be greater than or equal to all Lj's. This is the maximal length, obviously. If there is some equality involved here, so if this is the case, then obvious. Otherwise, else if there is some equality involved, so this is for some j's and Pm is less than all other Pi, so other I which is not equal to those j's, then it is possible that the length is maximum for some Pj. This, not this Pm, but rather some other Pj's which are also equal. Then what you can do without loss of generality, you can assign swap the corresponding two codes, and you can assign the maximal length to this PM. That does not alter any generality, because all of these are having the same probability. So you assign the maximum code word to this PM. Okay, so then it is possible that some LJ is maximal, then swap code of some that AJ and code of AM such that LM is maximal. This is the first step, where you assign the maximal LM to the last symbol, which is having the least probability. Next, since the code has to be full, so this length LM, the corresponding code word, should have a sibling definitely, otherwise the code will not be full. So there will be another length which will be same to this LM. So the LM minus 1 will be equal to LM since the code is full. Code book or code is full. There exists some LK which will be equal to this LM. It has to be there, otherwise there cannot be one maximal code. There has to be at least two. So the sibling will be there. Now this sibling, it will be the probability, it will have the probability prior to just greater than or equal to this PM. So that can be either PM minus 1 if PM is the smallest probability. If there is some equality, that PM minus 1 will be one of those PJs where there is some equality. So again, that can be any of these PJs, but without loss of generality, you can choose the PM minus 1 to be that. So that does not change any generality. So you can assign always LM minus 1 to be that LM. So you can swap those corresponding things. So then you can see that for this assignment, the last two code words last two symbols AM minus 1 and AM, for them you assign the code words CAM minus 1 and CAM. Both will be the siblings, and they have the maximal length, which is LM. Okay. Now you get the idea. From here we can apply the recursion, and we can write down the algorithm in a straight away, and I can argue towards the optimality as well. So now I can write the Huffman algorithm, I can say. So what Huffman algorithm does, it basically grows the tree in a reverse way. Starting from the leaf, it grows towards the root. So basically first order the probabilities. So have this ordering without loss of any generality, P1, P2 to PM minus 1, PM. Okay. So take the two least probabilities. Take the least likely symbols. AM minus 1 and AM. Okay. Then assign the maximal length. So maximal length means I will assign the LSB, the last bit, the right hand side bit. So assign the rightmost bit, which I can say LSB, the least significant bit, to them. So one of them will be 0, other will be 1, without loss of any generality. There is no restriction on which one will be 0 and 1. 0 and 1 are just two symbols, so one of them will be 0 and the other one will be 1. B1. Once that is done, then I am moving towards, so suppose this is 0 for AM minus 1 and for AM it is 1. Okay, these are having the least probability, the two least probability. Then I move towards the node. Okay, I assign this to be this node to be a combined symbol a m minus 1 dash. So like combine the two symbols, am minus 1 and am to define a new symbol, say am I can write 1 or something to write down that this is the first step. So symbol am minus 1 1 with probability, the sum with probability of am minus 1 plus probability of am, which I am writing as pm minus 1 plus pm. Okay, now I assign only the last bit. This is basically on the branch, the 0 and 1s are on the branch. Yeah. This is the LSB which has been defined. The earlier bits are not defined. So how to find out those earlier bits? Forget about this now. You have a new symbol, and with this, how many symbols are there in the original tree? M minus 1, because 2 are combined to get 1. So now you have m minus 1 symbols in the alphabet, and so you have the corresponding probabilities. So p1 to pm minus 2 and this probability. So what you have to do, you have to reorder the entire thing in a similar non-increasing way. So you have revamped, you have changed the alphabet again, and now reorder the probabilities. So I can write them to be p1 1 2 in the same way, p2 1 I can say. So some pm minus 1 1. So this is the first step. Then go to step, say this is step 1, this is step 2. Go to step 1. And how long it will run? It will run until you exhaust all the probabilities. So until you get this probability to be 1. So when you reach there, that will be the stopping. That is basically the root. So this is the algorithm. So how to ensure that this algorithm will be optimal? I can give you one quick intuition that this is indeed optimal. So again, this is coming from mathematical induction. So suppose Lm minus 1. So suppose Lm minus 1 means of this renewed alphabet, the length of that is minimum. Then Lm minimum, Lm average is nothing but Lm minus 1, the length. That length is basically for the entire tree up to this. Now you are increasing the bit for the two symbols by 1 bit for this and 1 bit for that. So this minimal will be this plus you are adding 1 bit extra for two symbols, and they are occurring with probability pm minus 1 plus pm. So this will be equal to Lm minus 1 plus pm minus 1 plus pm. And now this pm minus 1 plus pm, they are not dependent on any choice, they are given already. So this has to be optimal. So if this is minimum, then Lm will also be minimum. Now this is inductive proof, because how to check this is minimum? Again you have to go to Lm minus 2, and from there you have to bring to Lm minus 1, and gradually you can move to L1 or something. So in that inductive way we can show that if the previous one is minimum, the next one is also minimum, because the addition is just probabilities, and those probabilities are non-negotiable. It is fixed. Okay. So this is Huffman algorithm. So one thing to observe is that even if you check the lemmas and the corresponding observation and the algorithm, there is no reference to one Kraft inequality and second entropy. There is no reference. So this Huffman does not consider Kraft inequality and entropy. So let me give you one example of this Huffman algorithm, how this works, and this is really like genius of that young kid David Huffman, who found out that the method like needs only the probabilities, nothing else, and then like by running it you can find out the optimal code. So I'm giving you one example to show that how this Huffman algorithm works. Okay. Suppose some example. Let me take a bigger example such that you can find out the methodology properly. So how it really works. So suppose the alphabet is as follows. How many symbols should I take? 8. 8 should be fine. So A1, A2, A3, A4, A5, A6, A7, A8. So I know that fixed length encoding will be 3 bits. Okay, regular binary encoding. Now let us assume the probabilities to be P1 is say 0.4, 0.25, 0.15, so 0.8 already done, 0.1, 0.9 done, 0.05, 0.95 done, 0.02, 0.97 done, 0.02, 0.99, 0.01. Well, these are the probabilities. Okay, so this is P1, this is P2, this is P3, P4, and I have written in a non-increasing way, you can see. So I expect that the lengths will be non-decreasing. So this will have the minimal length and this will have the maximal length. Okay. So how to proceed? Start with these two. So step 1. Start with P7 and P8. So P7 and P8. A7 and A8. So I put it A7 and A8. And I assign the values 0 here and 1 here. So in the new symbol, what will be the probability here? If I write this to be say A7 1, this symbol is having the probability 0.03. And this is basically P7 plus P8. The probability is 0.03. Now you see the probabilities will be 0.4, 0.25, 0.15, 0.1, 0.05, but P6 is no longer prior to P7 1. It is actually the lowest probability. So P7 1 will enter here. So in the reordering, it will have a different order. So when you reorder, it will have, so P11 will be P1, same, 0.4. Then P21 will be P2, which is 0.25, same. P31 will be P3, 0.15. P41 is same, 0.1. P51 is also same, 0.05. But P61, I can say that this is basically P61 is changed, which is basically this probability. So this I can write is probability of A71, I can say. So this is 0.03, and P71 is the earlier P6, which is 0.02. So this is the new ordering. Now what are the lowest probability? Lowest probability are these two. So these two will create the next level of siblings. So next level of siblings will be, here it will be this is A6, so S12 A6, and this is A71. So this will be 0, this will be 1. Okay. So what is this? This is the new term, which is say A62, and the corresponding probability will be P of A62 will be P61 plus P71, which is 0.02 and 0.03, which is 0.05. Okay. Now this symbol, this tree will be grafted over there, because this symbol is here. This entire thing will be grafted here. I am showing you. So what is the next step? Now I have here I have total 7 symbols. In the next steps there will be 6 symbols, because 2 more are combined. So step 3. This is basically step 2. The step 3, they are combined again. So P12 will be, I can write in this way. In another way I can show you quickly. So let me show that here. That will be even easier. So 0.4, 0.25, 0.15, 0.1, 0.05, 0.02, 0.02 and 0.01. I can combine these two to give you the next value, which is 0.03. Okay. So where here this is 0 and this is 1. That is this combination basically. Now this will come before, prior to that. So I can write, I can take it this side, and these two I can combine now. So here I am giving 0 and here I am giving 1. So that will be my next step. So this point is basically A71, I can say. This point is A71. This point A71. This point is A62. Okay. Now A62 is having the corresponding probability 0.05. This 0.05 and 0.5 are here, so I can combine them here. So that will give me the probability of this is say A53, I can say, and this will have a probability of 0.1. Now this 0.1 and 0.1 I can combine here. This I am assigning 0 and this is 1. So these two if I combine now, so this will be A44 suppose, and that will have probability 0.1 and 0.1, 0.2. That 0.2 will come prior to this, so this will come from this side. So this side and this will come from this side. So these two will combine, and these two will combine to give you A3, say 5. This is the 5th step, and it will have the probability 0.2 and 0.15. That is 0.35. So 0.35 will come prior to this. So this will come this side, and this will come from here, and they two will be combined to give you the next like symbol, which is A26. Say this will come with a probability 0.25 and 0.35, which is 0.6, and this will be the largest now. So this will combine with this to give you the probability of 1. So here assignment is 0, 1, here assignment is 0, 1, here assignment is also 0, 1, here assignment is 0, 1. So this is the tree construction in every step, and we are doing the reordering. So I did it quickly. Now from here, if I write down the code assignment for the original symbols, this is A1, A2, A3, A4, A5, A6, A7 and A8. I can actually write down the tree in a better way now, starting from this root here. So from this root, so this is the 11, this is the root. So from that root, one side it is 0, another side it is 1. 1 is A1. So 1 is, this is A1. The other side it is 0, and from 0 you have 2 more. So one side is 1, another side is 0. So 1 it reaches to A2. The other side, the 0 side, will go to A35. So this point is basically A26, I can say. This is A26. This is, I can write as A17 or something like that, which is having one probability. This is A26. A26 will break down to A2 and A35. This point is A35, say. And A35 will again break into 0 and 1. And 1 goes to A3. And 0 goes to A44. A44. Now A4 will break into A44 will break into 0 and 1. And 0 goes to A4. And 1 goes to A53. A53 again like partitions into 2, 0 and 1. 0 goes to A5 and 1 goes to A62. This is A62. Now A62 again 0 and 1. 1 goes to A6. 1 goes to A6 and 0 goes to A71. And that again partitions into 0 and 1, A7 and A8. A7 and A8. So this is the complete tree. So in a much more tree-like structure, this is a little like visually non-appealing. This is much more appealing. Now from here you can construct the codes simply. So A1, the code is 1. A2, so code of A1 is 1. Code of A2 is 0, 1. Code of A3 is 0, 0, 1. Code of A4 is 0, 0, 0, 0. Code of A5 is 0, 0, 0, 1, 0. Code of A6 is 0, 0, 0, 1, 1, 1. 0, 0, 0, 1, 1, 1. Code of A7 is 0, 0, 0, 1, 1, 0. 1, 1, 0, 0. Code of A8 is 0, 0, 0, 1, 1, 0, 1. 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0. Yeah, 1, 1, 0, 0, 1, 1, 0, 1. So the lengths are, you see the lengths. For A1 the length is 1. For A2 the length is 2. For A3 the length is 3. A4 the length is 4. A5 the length is 5. A6 the length is 6. A7 the length is 7. 8 the length is 7. So these are the lengths, and from here you can compute the expectation of L. You compute and compute Hx also and compare them, although in the construction of the code you don't need Hx. Okay, you do one thing as well, that is from this probability just compute the lengths from this formula, that is log of pi minus log pi ceiling. So from there also compute the Li and check from here what is the like expectation of that length comes, and then you can compare this method with the Huffman method. So these three things you compare. One is using craft, you compute L, you compute Hx, and you compute EL from here. Okay, you will see that the Huffman performs better than this one, and it goes really close to Hx. Okay, so with this I stop. In the next class tomorrow I will be talking about source coding theorems. So we need one information theoretic result as well, which is called the asymptotic equipartition property, and using that we will start the source coding theorems. Then we will talk about the universal codes, because Huffman code is good, but the problem with Huffman code is that it is dependent on the assignment of the probability, and many a times the probabilities are not exactly computable. For example, some real life data, for example like text data, some novel, and you have some text data or some voice data or some video data. So you have to compute the probabilities empirically if you have the entire data available, but if the system is real time, you may not have the probabilities at hand. Then how to develop reliable source coding scheme which can bring the bit rate towards the entropy? And for that there is something called the universal encoding, which was developed by Zeeb and Lempel, and that Zeeb-Lempel algorithm is used in most of the real applications. For example, in Unix compression. So in your operating system there is some WinZip or WinRAR, even in Windows, and that application is there in Unix also. First time it was developed for Unix, so that Zeeb-Lempel was used in that compression. So compression is basically minimizing the bit length, the bit rate per symbol, you can say. So that will be our next topic. So for that we need some more information theory. So we'll start with asymptotic equipartition theory. Okay. So till then, bye. Please observe that how this Huffman algorithm is working, and I can share with you the text material from Professor Gallagher's book. You have the Prowaki's book as well. So Huffman algorithm is described over there also. Please go and read it. It will be really obvious. You will understand what is happening. Okay. So see you tomorrow. Till then, bye.